This resource is the fifth in a series on derivatives. We will explain the concept behind derivatives and formally define them. We will discover how to find the derivatives of various forms of functions, including polynomials and trigonometric functions. We will consider how to differentiate products, quotients, and composition of functions. We will also consider applications for derivatives and how they relate to real-world situations. Suppose we have two functions, which we will call u and v. Both are differentiable. Now suppose we form a new function f of x by dividing u by v. What would be the derivative of this function? We might be tempted to think that f prime would simply be u prime divided by v prime, but this is not correct. The actual derivative is more involved. To find the derivative of function f, we have the quantity v multiplied by u prime minus u multiplied by v prime divided by v squared. A way to remember this is the mnemonic low d high minus high d low over low low. Let's look at some examples. Recall that in the resource on finding the derivatives for trigonometric functions, we said that we did not have sufficient information to find the derivative for tangent. Well, now we do. Consider the function f of x equal to the tangent of x. Another way to describe tangent is to consider it as sine over cosine. So we will use the quotient rule to find the derivative. The function in the numerator u is the sine of x. The derivative u prime is the cosine of x. The function in the denominator v is the cosine of x. The derivative v prime is negative sine of x. Plugging into the formula, we have the quantity cosine of x multiplied by the cosine of x minus sine x multiplied by negative sine x, all divided by the cosine of x squared. Multiplying, we have cosine squared of x plus sine squared of x divided by cosine squared of x. One of the trigonometric identities is that cosine squared plus sine squared is always 1. So f prime of x will be 1 over cosine squared of x, which is also known as secant squared of x. What happens if we have an example that is not trigonometric in nature? What if our function is 1 over x raised to a positive integer n? The u is the constant function 1, which has a derivative of 0. The v is the function x raised to the nth power. V prime is n multiplied by x raised to the power of n minus 1. Plugging into our formula, we have the quantity x raised to the nth multiplied by 0 minus 1 multiplied by n times x raised to the power n minus 1 divided by x raised to the nth power squared. Simplifying this derivative, we are left with negative n multiplied by x to the power n minus 1 divided by x to the 2n. Because we are dividing powers with the same base, we can subtract the exponents. We have negative n multiplied by x raised to the power n minus 1 minus 2n. This leaves us f prime equal to negative n multiplied by x raised to the power negative n minus 1. But another way to write our original function is that f of x equals x raised to the negative n power. If we use the general rule for differentiating polynomials, we would have negative n times x raised to the power negative n minus 1. Oh, we did. This means that the general rule for differentiating polynomials works for any integral power of x, not just the positive powers. Let's look at one more example. What if our function is the secant of x? We can reimagine secant to be 1 over the cosine of x. Our function u is the constant 1. U prime is 0. The function v is cosine of x. V prime is negative sine of x. Plugging into the quotient rule, we have the quantity cosine of x multiplied by 0 minus 1 times negative sine of x all over cosine squared of x. Simplifying, we have sine x over cosine squared of x. This is the same as 1 over cosine multiplied by sine over cosine. So the derivative of secant of x is the secant of x multiplied by the tangent of x.